Hello and welcome to our investigation of the effects of mangrove fragmentation on the Bimini population of lemon sharks. This is by Sal, Devin and Emily. So grab your goggles, slap them on and get ready for a dive in with some lemon sharks. So on this first part we're going to look at the lemon shark biology, the importance of mangroves and the consequences of fragmentation. So now some simple biology for lemon sharks. Lemon sharks are easily recognisable from their yellow tinted skin, but we get some olive and brown skinned lemon sharks, but it's usually lemon or lemon coloured, hence where the name comes from. And they usually reach sizes of 11 feet long, 3.5 metres, and have few natural predators once they reach 5 feet. Now the natural predators are larger lemon sharks or bull sharks, which are an incredibly aggressive species. Both males and females tend to be sexually mature at ages 12 to 13 and usually are around 2.5 metres long, but they continue to grow until death, which is usually around about 27 years old. The females breed once per year and after 9 to 10 months of pregnancy give birth in nurseries. Now, the females take a year off after breeding to recover from the energy loss, meaning that they breed 1 year, give birth, and then take a full year out to recover the energy. Now, the nurseries are located in the mangrove forest of Bimini, which have a higher carbon dioxide percentage in the water. Now, lemon sharks, unlike most sharks, have the ability to increase their own gill pouch size by up to 20%. And this is very key for getting oxygen in high carbon dioxide areas. And lemon sharks usually give birth to 4 to 17 pups between April and September. So why do we keep going on about mangroves? Why are mangroves so important? Well, mangroves are incredibly important to the ecosystem around the world, and they cover an area similar to about 15 million hectares, which is intrinsic to carbon capture, providing nursery sites and providing food for the ecosystem. They also help humans out, and they do so by playing an important role in protecting humans from cyclones, tsunamis, and shoreline erosion. Now, for those that don't know what a cyclone or a tsunami is, it's a very, very big storm, and a tsunami is a very, very big wave, and they cause a lot of destruction. But with the mangroves bearing the brunt of the force, the extent of the destruction is a little bit less. Now, one such species that uses the mangroves, as you probably know by now, are lemon sharks. And they use it as a nursery site to feed and grow until they're strong enough to survive in the open ocean. So they are born, swim to the mangroves, stay there for about a year feeding on small fish or crabs, crustaceans, anything that they can actually eat, and then move out once they're a little bit bigger to, say, coral reefs, but still nearby the mangroves until they get much, much bigger to about 5 feet to avoid being eaten.
So when we look at the consequences of fragmentation, it reduces the functional connectivity of the mangrove systems, so the degree in which the mangrove landscape allows or doesn't allow the movement of the shark population to move along patches that contain resources like prey. And speaking of prey, it reduces the prey abundance in mangrove, seagrass and reef systems as well, with one study we found showing a strong positive correlation between prey abundance and large-scale shark distribution within the Florida Bay Area. And another study we found discovered that a high fragmentation rate in the Cà Mau province of Vietnam had biodiversity decreased by 1.78 times and had patch numbers increased by 58%. So obviously higher fragmentation. The water quality was also reduced as mangroves act as filters that filter out the contaminants and nutrients in seawater. The filtration rate was obviously reduced by the reducing mangrove cover. Fragmentation also reduces carbon sequestration, as mangroves contribute to 14% of all carbon storage in the ocean. This reduction obviously has a major impact on global carbon storage. It also reduces land resilience from natural events. So, for example, a study found that out of the 418 villages hit along the Andaman coast in the Indian Ocean by the tsunami in December 2004, only 30 to 37% of areas with mangrove cover were severely devastated. This contrasts to areas that had no mangrove cover because they've been transformed into aquaculture or tourism areas, and they received 80 to 100% devastation. So there's clearly a difference. And finally, what we found in the literature was the consequences fragmentation, there was an increase in light penetration, visibility, and reducing distance to open water from the nursery areas. And this led to increases in predation by open water predators on juvenile lemon shark populations. So obviously this isn't good for the population that we're studying.
Many studies were carried out to try to restore mangrove populations, mainly because of the importance that these ecosystems suppose for the protection of the coast. And this restoration affects not only for the mangrove itself, I mean the tree, but also for all the species that benefits from the resources that this tree generates, and species such as the one we're working on. And there are two principal measures to restore mangroves. First of all, the suspension of any destructive activity, like for example the construction of ludic and summer holiday places, which is the case here in the Bimini Islands. And there's a new technique that consists in the implementation of concrete anchors to help young mangrove establish and create a network of strong roots. And this study, for example, they found out that these structures help to resist since a 42% to 73% of the new mangrove to different hurricanes.
We're now moving on to our modelling and method section. So this is our modelling population. We use a single patch-based model, and our age structure matrix is ages 1 to 2 are young immature, ages 3 to 7 are older immature, ages 8 are the mature reproductive adults, ages 9 is the non-reproductive adults. Remember, they take a year on and then take a year off of breeding. Now our density dependency is 1b, is 100, and the number of individuals per hectare is 9. And this allowed us to get to a population of around 150 individuals in the area. And the initial ages are randomized. Now the numbers on the right are our survival rate numbers, and the large number at 7 at 8 over juvenile is the average we predicted the number of pups that a female will produce. Remember, it ranges from 4 to 17, so we predicted about 7, giving us a stable number to work with. We're now moving on to the results section, where we looked at reduced, current, and increased fragmentation. So mangrove fragmentation at the current rate sits at 30 to 35%. So we have 50 million hectares of mangroves left after 30 to 35% of their original population was destroyed. Now, the current population on the left is sat at 150, which is the population size of the Bimini lemon sharks at the moment. Now, if we were to keep all the survival rates the same and allow no outside factors such as hunting or oil spillages or disease affect the lemon sharks, the current growth is to peak at around about 500 individuals within 200 years, leveling out at around 400, which is really good for the survival of the species. It means that the population's healthy, it's growing, and that things are going well. Now, over a span of 1,000 years, it's a little bit different, but it's pretty much the same. The peaks at around about 650 individuals, stays around about 400, and is probably going down for another little dip like at the 500-year mark. And this is really good for the survival of the species. However, you'll see in the coming slides that changing just one little bit of fragmentation can have a massive effect on the species.
So when we modelled our lemon shark population to a hypothetical situation on if fragmentation increases in the future from its current 35% rate, these are the results we found. So with a 2% fragmentation increase, there was a significant decline, and the population levelled about 100 years, but continues a gradual decline after 150 years and goes extinct eventually at around 190 years in the future. With a 4% fragmentation increase, it's thought to be extinct at around 180 years, makes a small recovery at 198, but we're counting the population as extinct when reaching around 10 individuals because it's probably not a lost cause at that point, but it probably is a lost cause at that point, only having 10 individuals left to take over population. When looking at a 6% fragmentation increase, it goes extinct around 130 years. And when looking at an 8% fragmentation increase, it goes extinct around approximately 92 years. However, with a 10% fragmentation increase, it's extinct at 82 years, roughly. So from this, it's clear that by just slightly increasing the fragmentation rate on these delicate mangrove systems, this can have a devastating impact on the populations living there. And with lemon sharks being an apex predator, this extinction would lead to significant shifts in the ecosystem and possibly cause a top-down cascade on the trophic levels below. So this is a graph image showing the survival rates of each lemon shark life stage we found when looking into the literature of this Bimini population. I modelled it to compare current fragmentation rates around 35% against the extreme case of fragmentation rates doubling, which would be around 70%. So as you can see here, there are significant differences between the survival rates across all the life stages. So as you can see with the juvenile population, for example, it starts, well, currently it's at about 0.62, which is relatively good at the minute. However, if the fragmentation rate was to double, this would go down to 0.3, so this is over half, over 50% of a decrease, which would subsequently have a chain reaction on all the other life stages, so the mature and the adults. So like the increased rate models I showed you before, this again shows that if we continue to increase our fragmentation rates, our lemon shark population will most likely half in size, and with most individuals leaving the area in search of more suitable nursery grounds. This will cause a shift in the natal or ecosystem that they were originally in, but also the ecosystem that the sharks move to, since there'll be an extra productivity pressure due to more apex predators present. So ideally, we don't want to increase fragmentation rates because this will have subsequent consequences on the ecosystem surrounding the area.
What would happen if the fragmentation began to decrease? So with just the 5% of decrease in fragmentation, the population would increase till 600 members in the first 200 years. With the 10%, the population would increase till 800 members approximately, and in a much better scenario, with a 30% in reduction in the fragmentation, the population will increase more than 1,400 members in just 80 years. A hypothetical scenario where there was no fragmentation, and with this I mean without any extra mortality rate like fishing or mortality caused by diseases, the population would increase to 1,600 members in less than 80 years. This basically means that if some areas would achieve this level of fragmentation, so considering the area or the implementation of a reserve, the population would be able to increase and continue growing until the total capacity of the ecosystem. So finally, as conclusions, with our rainshifter models, we've been able to recreate what would happen if the fragmentation of our mangroves changed. In our case, in the one hand, increasing fragmentation rate by 10% will result in extinction of the species of this population within 85 years, and doubling current fragmentation rates will most likely result in the population size decreasing to half of the current numbers. And on the other hand, decreasing fragmentation would overall make the population increase. In a hypothetical situation without any fragmentation, the population could increase almost 16 times, which is a big change. And with all these results, if we want this population to stay alive, we would want to decrease the fragmentation of the ecosystem, of course, and there are sufficient measures that could be applied in order to achieve this.
So thanks for listening, guys, and let us know if you have any questions.